Definite integrals add another step of placing values into the solutions to have a numerical answer instead of a function. Welcome to Integral Calculus. Definite integrals can be described as those antiderivatives with upper and lower limits. So if we compare, an indefinite integral has its standard form as the integral of the differential of x dx, which equals to the function of x plus the arbitrary constant c. In a definite integral, the differential will be integrated with upper and lower limits of b and a, which results to the antiderivative using b for x less the same antiderivative using a for x. With these two configurations, one note is to have upper and lower limits for definite integrals, and placing particular limits would eliminate the arbitrary constant in the final answer. There are some basic properties of definite integrals which are worth checking right now. First is if the limits of the integrals are interchanged. Say first is with limits from b to a, having them interchange into upper limit of a to lower limit of b. These will be equal numerically, but with opposite signs. Graphically, the antiderivative is the area limited by b and a, where computation will be taken as opposites. For example, take the antiderivative of x squared dx, which is solved as x cubed over 3 with limits from 3 to 1. So working with the limits, we get 3 cubed over 3 less 1 cubed over 3, simplified as 26 over 3. Similarly, take the same integral but the limits reversed, from 1 to 3. The antiderivative of the function will still be x cubed over 3. Then plug the limits to get 1 cubed over 3 minus 3 cubed over 3, resulting to negative 26 over 3. The next basic property is when the upper and lower limits are the same, saying the integral of f of x dx from a to a, and this will be equal to 0. Graphically, this can be explained as the area generated below the curve from x or a to a, which will be basically just a line, having no area at all. For our numerical example, take the integral of x plus 5 dx from 4 to 4. The antiderivative of the differential becomes x squared upon 2 plus 5x, where the limits are from 4 to 4. Plug these limits and get 4 squared over 2 plus 5 times 4 minus the same quantity as the lower limit is also 4, leading to the answer of 0. Another basic property is the integral of a function x from b to a, plus the same function having limits from c to b can be reduced to the integral of the function from c to a. Graphically, we can explain the property by checking on the areas. So with limits from b to a, we get the first area. Then with limits from c to b, the next adjacent area is considered. So focusing on the areas, we can say that the total area is taken from the range of c to a. For an example, let's prove that the summation of the antiderivatives of x plus 1 dx from 3 to 1 plus the same antiderivatives from 5 to 3 is equal to the antiderivative from 5 to 1. From the left side, The antiderivative is x squared over 2 plus x from 5 to 1. The limits can be placed to the antiderivative as 5 squared over 2 plus 5 minus 1 squared over 2 plus 1. Simplify the brackets and get 16. Now check the left side of the equation. The integral turns out as x squared over 2 plus x. Then all we gotta do is to plug the limits. That is, x squared over 2 plus x with the limits from 3 to 1. Then add the second term as the same x squared over 2 plus x with the limits from 5 to 3. Simplify the brackets and have 6 plus 10, which is also equal to 16. The next basic property is the integral of a constant times dx from b to a as equal to the constant c times the limits b minus a. Graphically, this cannot be shown clearly, but then we use an example to prove this property. Take the integral of 6 dx from 3 to 2. The antiderivative is 6x with the limits from 3 to 2. Thus, the limits are placed as 6 times 3 minus 6 times 2, which is equal to 6. The right side of the equation is c times b minus a, where c is 6 and this is multiplied by 3 minus 2, or that is 1. So, 6 times 1 is also equal to 6. Another basic feature shows the distributive property of the integrals. Say the antiderivative of two functions, f of x and g of x, which have the same limits from b to a. This can be separated into the integral of f of x dx from b to a plus the integral of g of x dx from b to a. Let's prove this property with a simple integrand. Take the integral of two terms. One is x over 2 plus 2, then the other is x squared plus 2x, with the same limits from 3 to 0. Take the antiderivatives and have x squared over 4 plus 2x plus x cubed over 3 plus x squared from 3 to 0. Plug the limits and have the first one as 3 squared over 4 plus twice of 3 plus 3 cubed over 3 plus 3 squared. Then plug the lower limit and have 0 squared over 4 plus twice of 0 plus 0 cubed over 3 plus 0 squared. Both these terms can be simplified as 26 and a quarter minus 0, thus having the answer 26 and 1/4. The right side of the proof then starts with f of x, that is, x over 2 plus 2 from 3 to 0. Then the second term is x squared plus 2x, and both are with the limits from 3 to 0. The antiderivatives of these terms are solved as x squared over 4 plus 2x from 3 to 0, plus the second term has x cubed over 3 plus x squared from limits of 3 to 0. Plug the values and get the first term as 3 squared over 4 plus twice of 3, minus 0 squared over 4 plus twice of 0. Then add the second term, being 3 cubed over 3 plus 3 squared, less the lower term as 0 cubed over 3 plus 0 squared. Simplify the first term as 8 and a quarter, minus 0. The second term is 18 minus 0, having 26 and 1/4, which is equal to the left. The next property can be interpreted using the areas. First, if the integral of a function from limits of b to a turns out as greater than 0, or positive, the area is drawn above the x-axis. Otherwise, the area will be treated as negative or below the x-axis when the integral from b to a results to a value less than 0. And yet another property is again shown graphically, where the limits will be crossing the x-axis. That is, there are two areas involved. One is positive and another as negative. The integral of the function within the limits is computed as the area above the axis minus the area below, which can be simplified as the net area. Again, this is true only for continuous functions.